not that bad to work with. But if you don't get that, you're going to get swamped later on in the chapter, because it's not do section 1, forget about it, move on to section 2. It's do section 1, take what we learned in section 2 or section 1 and use that for section 2. So we're going to start in 2 dimensions and eventually go to 3 dimensions. Staple your work in the back and throw that in there too. Okay, so we should, we're going to find the area between 2 curves. Again, easy concept today. You can probably teach the lesson to me, which would be fun. We're going to find the area between 2 curves using integration. We're going to look at what happens when the bottom changes. So you got one function above another function, but what happens if in the interval the top becomes the bottom and the bottom becomes the top? How do we handle that? And then we're going to go back to that concept of the integral being an accumulator, so it adds up a bunch of things. It's going to become particularly important in chapter 7. Okay. And you should be able to make good scrambled eggs. Anybody? Good. What's the secret? Oh, wait, hold on. Milk or water?
Milk.
Milk, right? You need some protein. And the biggest problem is people overcook.
Eggs don't have enough protein.
It also just makes it taste better.
Yeah.
Right. Yeah, it's got a little bit of oomph. Okay. Some would argue, however, if you add water, they're fluffier.
You gotta put butter in the pan before you cook it.
Yeah.
Butter and milk and eggs. Just load it down.
And tacos. Tacos in the pan are good too. Sugar? In your scrambled eggs. That sounds good. Okay, so blah, 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 blah. Well, if you can see my computer right now,
Yeah.
you would notice that this region is actually pink. So you're going to have to imagine that that's the region we're looking for. Okay, I want to find the area of that thing. So let me give you a shot first. How would you go about finding the area of that supposed to be pink but didn't show up on the projector screen region? Greg?
Would you find the area above the blue curve within the boundaries and then below the black curve in the atom? Or do something like that?
You're close. Luke?
Find the areas below both of the curves and then subtract the blue one from the black one.
Why? Just kidding. You had like an ephany there. Like
I don't know how to explain.
Because
the
then
math gods have blessed me with the correct answer. Hey guys, what do you want to contribute here?
Well, going back to what Greg said, if you took it the area above the blue curve, that's.
Do we know how to find the area above a curve?
You can take the area above the black curve and then take the area below the blue curve and subtract.
Find the areas
exactly
below
what Luke
both
said.
of them
Yeah.
and then subtract.
Dante's trying to steal your glory, man.
Hey,
He just repeated
I
exactly
was
what you
nervous
just
with the
said.
knowledge, not you.
Okay, so then we'll go back and we'll see if that works. So blah, 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 blah. Okay, couple terminology terms. Couple terminology terms?
yes.
A couple, never mind.
Redundancy.
Hey, we got some terminology to talk about. We talk about this concept of being bounded by. Bounded means starting and stopping or restricted in an area. So we're going to talk about the region between the 2 curves that's bounded by the values of A and B. If it's not bounded, it means it goes on forever. So if you look, this triangular, pseudo-triangular region over here is unbounded because it keeps getting bigger and bigger and bigger. So the area between those curves would eventually be infinity if you don't stop it anywhere. However, this little cat's eye shaped thing is a bounded region, and we can bound it further by restricting it with a starting and stopping point. Okay? And then we use no intervals and blah, 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 blah. Great. Okay. What's that? Well, that is, again, not showing up on the graph. This technology is killing me. Okay.
Get it together.
Are we blaming Mary for this one?
Oh, yeah.
All right. Way to go, Mary.
What else is new?
Yeah. So since f of x is the black curve, then the integral from a to b of f of x would be the area from the black curve down to the x-axis, because that's how we defined an integral. Right? It's the area under a curve. Any problems there? Good. Then, yeah, we talked about that already. And then g of x is the stuff below g. That one showed up because it's in blue. Note to self, don't use pink anymore. And so the region that we're looking for would be, as Luke said, the difference between the two. We'd get that. Okay. Perfect. And again, if you could see my computer, you'd see that's a really cool pink region. But it's not showing up there. I don't know why. For some reason, it's chosen to exclude anything in the red, but that red showed up. I don't know. Whatever. Let's move on.
So instead of finding the integrals of both, you could just find the functions, subtract and take the integral of that.
Excellent question. Everybody hear that? He said instead of finding the integral of both, just take the two functions, subtract them, and take the integral. Why does that work? Well, actually, what we're doing is this. Right? Well, we can sandwich it together because we have the same limits of integration. Because remember, we normally do the other way. We usually take this function, this integral function, and split it into two separate. We normally go that way.
Yeah.
This time we're going backwards. Just sandwich it together. So you only have to do one integral. Especially if you're doing like fn int and stuff, you don't have to worry about it. Done. Maggie?
So you can just take like the non-integral of f of x minus the non-integral of g of x and then take the integral of that?
Yeah. Subtract the two functions,
Okay.
take the integral,
Okay.
which will make our lives a lot easier.
Yeah.
Especially if the functions play nicely together, that when you subtract them, you'll be good to go. Okay, so there's the fancy calculus speak. There's really nothing important there that you haven't already talked about. Well, I shouldn't say that. There's a couple things. First of all, it mentions in there that it has to be continuous. That should make sense. If all of a sudden there's a vertical asymptote flowing through that, it's going to screw everything up. The other thing is they've got g of x being less than or equal to f of x. So what we're establishing is that we definitely have a top function and we have a bottom function. Then we've got the bounded a and b, and then everything else is what we've already talked about. Okay. Capital A stands for area, not lowercase a. That's going to become important, or it already is important as we move through this. Because eventually we're going to change the capital A into a capital V because we're going to be finding volume. This is going to be fun. Okay, so remember I talked about the building process. If I go back a couple slides, we're going to take that region, which again you can't see, and spin it around the x-axis and talk about the three-dimensional shape that you would get. What would that three-dimensional shape look like? Just take a moment and visualize. A weird donut, correct. It'd be like a donut with the top and bottom cut off because it wouldn't, you know. Yeah. So we'll be talking about the 3D stuff of when you take regions and spin them around, but that's not for a while. This is big. Top minus bottom. That's a mantra that you're going to use all the time when doing area and volume. Top minus bottom. In fact, it's so important I made it change colors.
That red showed up.
There you go.
That
Okay.
red showed up.
What's that?
That color red showed up.
I know, I don't get it.
Well, the
Is
one
that
there
red?
looks pink.
Maybe it's because it's not pink.
Or no, it looks like
You think,
red.
I'll test it to
It's
see
like
red
too
okay,
bright.
pink bad?
It's
Maybe.
like too light. See what you can see the reflection.
Okay.
Like, from the-
Top minus bottom.
Oh, yeah.
We good?
But like, I'm hand barely.
Okay. So, accumulator of stuff. We talked about that already, but it's especially gonna become important when we start doing this. And as we do this, a lot of the steps that I'm gonna do initially, you're gonna think, well, that's stupid. Why do we have to do that? But if you do it now, and it seems stupid, when you get to the complicated stuff, that stupid stuff becomes very relevant and will make your life a lot easier. Okay, so new terminology, representative rectangle. So here's this funness going on here. I've got a red function, I've got a blue function. Red showed up, it's not pink. And it's bounded by A and B. And so that cross-hatched area is the region I want to find the area of. So top minus bottom. So what I throw in there is that little vertical black line there. Okay, that's a representative rectangle. So you're saying to yourself, self, that doesn't look like a rectangle. Well, it is. But it's a really, really skinny rectangle. And how skinny is that rectangle?
Infinitely skinny.
Infinitely skinny. So if that rectangle is infinitely skinny, how many of them do I have from A to B? Infinite, right. And that's why we use the integral. because I don't want to manually add up all those rectangles. And if I make the rectangles really big, my answer is not going to be perfect. And I want it to be perfect because that's what we strive for all the time. Okay. So again, it seems silly to draw this representative rectangle because I can just take top minus bottom and go to town on the integral, but we're going to get in the habit of using this representative rectangle. And notice the height of that rectangle is f of w minus g of w, and w happens to be the point where I chose to draw my rectangle. You can draw the rectangle anywhere you want.
That's the height.
That's the height of it. How wide is that rectangle? What are we going to use to represent the width of that rectangle? And this is one of those puzzle pieces that fits together. No clue?
Limit?
I'm sorry? Who's talking?
A limit?
We don't want to open that can of worms, do we? No.
I don't.
Some people actually gag when you use the L word. Right? Watch. Limit. Yeah. Yeah, see? Smaller and smaller and smaller until it gets infinitely small. And so what we're going to do is use, okay, so I'll show you as we work through the problem. So here's an actual problem that you can see. We're going to calculate this. Sometimes on the problems, they'll tell you the point of intersection between the two graphs. Because again, we can only find the area for a bounded region. We have to have an enclosed region. So it's either going to be bounded by vertical lines because it says go from A to B, or like in this case, it just says the area bounded by the two regions. Very simple functions, x squared and the square root of x. I just zoomed in on it because notice I'm going from 1 to 1. First thing you may need to do is find the point of intersection. How do you find the point of intersection between two functions? Set them equal to each other. Set x squared equal to the square root of x, solve. And you find that that's 1 comma 1. I'm going to save the business there. We'll go on to 2. Draw your representative rectangle. Somewhere in the region that you're talking about, you need to draw a little vertical segment. Mine happens to be green. And you don't have to draw a rectangle, just draw a segment. Because we're talking about a rectangle that's really, really skinny.
Wait, does it matter where we put it? Did you say?
Nope, as long as it's in the region we're talking about. Okay, so now this requires a change of thought process here. Instead of finding this entire area, I'm just going to find the area of that rectangle. That's it. Okay? Then I'm going to use calculus to add up all the infinite number of rectangles. Are you with me? Kinda? All right, how tall is that rectangle?
Square root of x minus x squared.
Good. Square root of x minus x squared. Let's take a break. Everybody understand that? If not, speak now or forever hold your peace. Okay, so he said square root of x minus x squared. Now where does that come from? That's the multicolored buzzword top minus bottom. That's where that comes into play. That's the height. How wide is it? Well, again, we need to come up with a way to address the width of that. How do I represent something that's infinitesimally small? We're going to talk about it being so small that it becomes a differential. We're going to call the width of that rectangle dx. Okay. Now, why dx? Because we're working with a width here that goes along the x direction. Later on, we're going to talk about different rectangles. This one is a vertical rectangle, but the width of that goes along the x-axis, so it has a width of dx. A height of the square root of x minus x squared, a width of dx. So that's the area of one triangle.
Can you say again why it's dx is the
Hold on. Okay. So this is top minus bottom, also known as the height of the rectangle, and the dx is the width. Okay, we don't want to call it x because x implies that you're taking a numerical value. We don't know the numerical value. It's just really, really, really tiny. How tiny? It's so tiny we're just going to use a differential to represent it. Okay, so dx is going to stand for a really small value. In simplistic terms, this is height times width, or length times width, or base times height, whatever you want to use for the area of a rectangle. Okay? Now we good? That's algebra and geometry. Now we bring the calculus in. So because the integral is an accumulator, I can add up all those infinite number of rectangles. You may have put your rectangle over here. You may have put yours over here. It doesn't matter where you put it. There's an infinite number of them. So we want to integrate them. And integrating is going to add up all those rectangles. And we're taking rectangles from where to where? Well, we know we're going to start here at 0, and I'm going to continue adding rectangles moving to the right until I get to 1. Hey, how's everybody's day going?
How are you?
Oh, it'd be better if my pen was working. Oh, there it is. Okay. So top minus bottom, dx stays there. Why is the dx there? Because when you do an integral, you got to have a differential. You got to say what the variable is. Our variable here is x. Wow. That was awesome. Let's try that again. Jumped about 4 slides ahead. Okay, so before I move on, I want to make sure you understand how that works. And if you don't, then I'll go over it again. Yes or no? I got it. I got a lot of confused looks. I got no response.
Let's go again.
Go again. Okay, so the concept is going to revolve around this. Find the area of the rectangle, add up all the rectangles. That's it in most simplistic terms. How do I find the area of the rectangle? The height of that rectangle is top minus bottom. That's that mantra that comes up over and over again. Its width is really, really skinny, which we're going to represent with dx. So I start by finding the area of this representative rectangle that I drew. Plug in the functions. I mean, you probably don't need the first step. You can go right to the functions because you're all bright. And then take the integral. And the integral is I'm going to add up all the rectangles from 0 to 1. Pregunta.
So this is just the derivation. Well, like, or the integration, like the steps, like that gets you to the, like the equation, integral of a to b f of x minus g of x dx.
Yes. So when you do the problem, what you're going to do is you're going to draw your representative rectangle. You're going to say the height of that rectangle is square root of x minus x squared. You're going to take that whole thing, multiply it by dx, so I need the width of the rectangle. I'm going to integrate from the starting point to the ending point.
So we have to draw the rectangle.
Yeah.
Okay.
Yeah. You're going to, because especially because we're building on what we're going to do in the future, I want you to draw that rectangle. Okay? Just for practice, get out your calculators. We won't go through the hassle of actually doing it, I don't think. I think we'll just FN int that bad boy. So go ahead, FN int it. Well, that's a good thing we're doing it then. Okay. Math 9.
Reading. We don't have like a fancy calculator, like.
Okay, so if you're going old school, I'm going to try using the pen just because I'm self-abusive today. It would be FN int, comma, the function. So in this case, you would do square root of x minus x squared, comma x, comma 0, comma 1. So it's the thing you're integrating, comma, the variable that you're using, comma, the lower limit of integration, comma, the upper limit of integration. All right, what do you got? 0.33333. Does that answer seem reasonable?
Sure.
Yeah, who knows? You know, if you got something like 4,000, that's probably wrong. The area of this little weird eye-looking thing or leaf-looking thing going from 0 to 1 is not going to be 4,000. Okay, so just check to make sure that your answer seems reasonable. All right, we good? All right, so how can we, well, let's see what we're doing next. How can we make it more complicated? Well, we can do two things. We'll start with the less complicated, and that is what happens when the two functions cross over each other. Or the easier question you're going to ask yourself is what happens when the top or bottom changes? Okay, so blah, 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 blah. There's our example. This is easiest to see with an example. To save you the hassles, I have a picture of that already. So the red, well, you tell me. Which one's the red function? First one. Which one's the blue function? Wait, hold on. I just said which one's the blue function, and you said the green one? What's wrong with you?
I was looking at the second function on there, just thinking, oh, I'm going to do it in order of what's written up there instead of
Gotcha.
colors.
Okay, cool.
That's my excuse.
Let's try that again. Which one's the blue one?
The third one.
The third one, right. There you go. And that makes the green one this guy. Okay. So notice if I start over here on the left at this first point of intersection, you could read it off the graph. We're at negative 1, 2, 3, 4, negative 4, 2. Or you'd have to calculate it. Well, how would you calculate it? You take that function, set it equal to that function, and solve for x. Okay, set the red equal to the blue, solve for x. Not a difficult calculation, pretty straightforward question.
Will we have a graph every time?
No, not every time. Sometimes you will, sometimes you won't. This one I probably wouldn't give you a graph because these are all functions you could easily work with. Okay, so if I start from this point of negative 4, 2 and I start going to the left, you'll see what happens when I hit the y-axis. The top stays the red function the whole time. No problems there. But when I get to the bottom at 0, 0, the bottom of the function changes. It changes to the green one. How do you address that? Simply put, you do two different integrals. Okay? So let's try R1 first. What integral will you use to find the area of the first region R1? Before you answer, let me put in my representative rectangle. Doesn't matter where you put it, I'm just going to slap it in there. So, question number 1. What's the area of that rectangle? But we'll do that later. Just tell me the area of the rectangle. Good. Everybody hear that?
No.
It's a simple question. Did you hear him?
No.
Okay. Say it louder.
X plus 6 minus negative 1 half x. Just x plus 6 plus 1 half.
That's the height of the rectangle. Where did that come from, Dante?
Top minus
Top minus bottom. Again, that mantra pops up again and again. How wide is that rectangle, Dante?
d of x.
And I want to add rectangles from where to where?
Negative 4 to 0.
Negative 4 to 0. Okay, let's stop and take a breather. Are we good? That gets me up to the y-axis. Now I got to do the other region, which we call R2. New representative rectangle because a new region. In fact, I'm going to draw a different color in there just because I'm feeling saucy. Sid, you ready? Beautiful. What's the area of that blue rectangle?
X plus 6 minus x cubed
And how wide is it?
dx.
Beautiful. And I want to add rectangles, blue rectangles from what to what?
0 to 2.
Yep.
Yeah.
Well done. Now, depending on the problem, depending on what you're doing, you either simplify the functions and do it manually, add it all up, or you FN it the snot out of both of them. So, for instance, you could rewrite this as going from negative 4 to 0 of 3 halves x plus 6 dx, and this one would simplify to, actually it wouldn't simplify that much, would be negative x cubed plus x plus 6 dx. Each of those integrals you should be able to do by hand. There's nothing that difficult there. No UDUs going on. It's just take the integral of each of those or just plug them into your calculator. FN each one, and then remember the answer to the entire question then, the total area, whoops, I want an area, not a region, sorry. The total area would be equal to the area of R1 plus the area of R2. If the top and bottom change, you need a different integral. Because your rectangles are going to change. And if the rectangle changes, then you got et cetera, et cetera. I'm skipping the business about solving the integrals because I'm assuming that you're good to go on that. Is that a safe assumption?
Yes.
Beautiful. Because they're not difficult functions. I intentionally picked non-difficult functions so that we can talk about the area not getting bogged down in finding integrals. Can I erase this?
Yeah.
Everybody good?
Yep.
I don't know, can I erase this? There we go. Oh, wait, oh, look at, I did it already. Oh, F and N, yeah, so. Okay, now, what time are we out of here, by the way?
40.
All right, let's start and see what happens. What happens if we can't use vertical rectangles? Or what happens if we realize that we can use vertical rectangles, but horizontal rectangles would be easier? Sometimes people struggle with this, other people can see this. It's entirely up to how you're going to process this. So the concept is easy. Instead of working in terms of x, we work in terms of y. And so we'll have horizontal rectangles, which means it'll no longer be top minus bottom. It'll be right minus left. So we have a new mantra now. If you're working in terms of y, so here's my example. If you're working in terms of y, you're going to go right minus left, which I'll get to in a second. So I've got these two functions that are in terms of y's. I don't know why I wrote this one the way I did. I probably wanted to do this as 2y squared minus 4 equals x. Now, why would you work in terms of y? Why would you work with horizontal rectangles when I could just do vertical rectangles? There's a couple answers. Number one, you see if I solve for y in each of these functions, I get some ugly things that I don't really necessarily want to take the integral of. Or, more easily, if I do it using vertical rectangles, I need 3 different integrals to solve this problem. This one all the way to the left goes from blue to blue. So you got to figure out, well, how do I do top minus bottom when it goes from that to itself? So you got to play with pluses and minuses and all that other gunk. Then if you look at this little region over here, well, that's doable. You know, that's blue minus red. That's okay. Now on the bottom here, it's red minus blue. And then I got to set up 3 different integrals, and it becomes a pain in the butt.
Mr. E.
I know what you're going to ask. Go ahead. Wait, you want me
Yeah,
to see if
yeah.
I know what you're going to ask? You're going to ask, well, wouldn't the area below the x-axis be negative and the one above the x-axis be
Yeah.
positive? They're the same region. Why wouldn't you get an answer of 0?
Yeah.
It's a great question. The answer is when we do this kind of stuff, areas and volumes, there's no longer an idea of negative area. So we take that concept of negative area and we throw it out the window. This has a positive area down here. This has a positive area. Well, there's some other ways that we can cheat. And before we get to horizontal rectangles, what I could do is just find the area above the x-axis, stop my rectangle there, find the area of that region up above and double it because they'd be the same. But what you'll see is that if I do it in horizontal rectangles, I need only one integral. Because this yellow rectangle can be slid all the way up here, or I can slide it down there, or I can slide it down there. But I still only need one rectangle because the right never changes, the left never changes, and therefore one integral will get this done.
So dy, just change it to
Right. And your function should be represented in terms of y. Okay. So horizontal rectangles just means instead of top minus bottom, we do right minus left, and instead of working with x's, we work with y's now. Okay, so I'm going to go from 2 down to negative 2. The right function is the red one, which is this one. So I would do y squared minus the other one. I think I have that worked out here. Yep, there we go. Okay, so right minus left. Start by finding the point of intersection of the graph. Well, they're easy to see because they're on there. That's 1, 2, 3, 4, 2, and 4, negative 2. But we want the y values there, so we're going 2 and negative 2. Okay, am I going too fast? Is this sinking in?
Would it be 2y squared minus 4?
Yes. I don't know why I wrote the function that way. Okay. There you go. Points of intersection, which you can all do. You're bright enough to do that. Okay, let's get to the fun stuff. Okay, area of the rectangle. Right minus left. The right function is the red one, which is y squared. The left function is 2y minus 4. Subtract those. Be careful with parentheses. These parentheses are very important because you're going to have to distribute the minus sign. And because we're working with horizontal rectangles and everything is in terms of y, you have a dy. Okay. So horizontal will always be in terms of y. Vertical will always be in terms of x. If you set it up and you've got x's over here for the height of the rectangle, and you've got a dy, you've done something wrong. If you've got y's over here and you've got a dx, you've done something wrong. You will never have a problem that combines those two, because we've talked about this before, but I'll ask again, what's the integral of y squared dx? For those of you that are visual learners, let me write that down. What is the integral of y squared dx? Right, what'd you say?
Y squared x.
Y squared x. Why? Oh, plus c, just to get everything above board.
Because the variable is x and you don't have that in there, so you're just gonna add x on.
Right. So that's considered a constant in this scenario. That's why you're not going to have this. So again, something else to process here. Horizontal rectangles, everything's in terms of y, including the dy. Vertical rectangles, everything's in terms of x. Y's and x's don't play well together in this stuff.
But if you keep integrating, just keep doing it.
You're not helping. Okay, so we get that whole business going from 2 to -2. Sometimes people struggle with the limits of integration. So think about where you're sliding this rectangle from, and or possible locations you could write that rectangle or draw that rectangle. The highest point I could draw that rectangle would be up here at 2. And I can draw rectangles all the way until I get down to -2. Okay.
Why is it right minus left? Why is it right minus left?
Because now we've taken our rectangle and tilted it over. So now our rectangle runs this way. And we're actually going to do width times height. But the height is real tiny. And so the width is the right minus the left. Okay, top minus bottom if you're working in terms of x, right minus left if you're working in terms of y. We okay? A lot of information, I know. We're done. Okay. I don't know why I put a picture of a granny dancing, but
Wait, can you go back to
Can we
Sure.
You want us to solve the